Hello everybody and welcome to AP Physics 2 where everything's made up and the points don't matter. Do you even get that reference? Look it up. Alright, anyway, we last left off talking about nuclear decay. And we learned that there were three methods by which this could happen. There is alpha decay, where we emit a helium nuclei. So it has a charge of +2 and an atomic mass unit of 4. So there's 2 neutrons, 2 protons. We have beta decay, where we can emit a electron, which has a charge of ±1, depending on whether a positron or an electron was emitted. And we have no mass change. So the beta particle has no significant mass. The electron, yes, it does have a mass, but it's about 2,000 times smaller than either a proton or a neutron. And so for the nucleus itself, the mass doesn't super change that much. And then lastly, we have the gamma ray, which is just a photon with no charge and no mass. And therefore, the gamma rays are able to penetrate through things the most readily. So these are our three mechanisms by which a nucleus can decay, but we haven't really talked quantitatively about how to model, the nuclear decay of a sample. So we're going to briefly talk about that to finish up our discussion on nuclear physics, and then we'll move on to the juicy subject of quantum mechanics. All right, so what's observed for any of these three mechanisms is that we're kind of out of focus. Let's see if we can do a little bit better by you. All right. All three of these mechanisms can be modeled by essentially the same equation. What's observed is that for any nuclear sample, after a certain amount of time, half the sample will have decayed. We call this certain amount of time, and it's a special property of any particular kind of radioactive nucleus. This certain amount of time is called the half-life. We symbolize that by T with a subscript a half. It is the time for a sample to reach half its original amount. We're going to relate this half-life, T half, equal to the natural log of 2. And this is just because, essentially, it's decaying exponentially. After each half-life, you only have half of the sample left. We want to model that with an power e exponential function, and this ln2 helps us make that conversion. Divided by this lambda here, which is known as the decay constant. And this is a property that will be different for each radioactive isotope. If we have a certain number of nuclei we started with, and 0, we could figure out how many we have left as a function of time by the following relationship. We have our starting coefficient, n0, multiplied by e to the minus lambda t. Or we could rewrite this as n0, e minus lambda is equal to ln2 divided by our half-life. So this function is actually exponential. You may call it as such. It decays exponentially. For every half-life that passes, we end up with half of the amount we started with. And that's the real key here. I think very rarely on the AP exam, they would ask you to solve for the exact number of particles, but you can use this idea of a half-life to get to a rough estimate. So for example, if I start out with 10,000 atoms in my sample, and we're told that we have a half-life of about 5,700 years. So T half equals 5,700 years. This is pretty close to what you'd expect for something like carbon-14, which is used in a lot of radioactive archaeological dating. if I want to know when I have about, 2,500 atoms left, well, that's a quarter of what I started with. So I end up with a quarter after, so after one half-life, I get half of what I started with. So that's one half-life passed. After the next half-life, I'll have again. And after the next one, I'll have even further, 1,250. So this is 5,700 years past. This is another 5,700 years. This is another 5,700 years. So after 10,000, 1,400 years, I will end up with the desired amount of atoms left. 2 half-lives has passed. If I had something that wasn't exactly a quarter of what I started with, maybe it asked for about, 3,000 atoms left. Well, 3,000 lies somewhere in between, this first half-life and the second half-life. So I know, at least 5,700 years have passed. And I know the total amount of time has got to be somewhere between twice the half-life and one half-life. So the answer to this first question is 11,400 years. So you can use this idea that whatever the half-life is, I lose half of my atoms to get, a rough estimate of how many atoms you have left. If you really wanted to go in and solve this exponential, you're welcome to do so. But again, very rarely do they ask you to be that specific. All right, so that's our nuclear decay. That's the end of that topic. Moving on, we're going to move into quantum mechanics. We've already seen little traces of this already when we talked about the photoelectric effect. We said that, once we reach a certain threshold frequency, HF0, we could liberate an electron. If we increase the frequency, we increase the energy of the photon, but we don't get more electrons released. So it's essentially we get one photon in, one electron out. If our frequency is greater than the threshold frequency, the resulting electron has more kinetic energy. So the conclusion of the photoelectric effect experiment is that light behaves like a particle and its energy can only exist in a specified quantized amount based off some multiple of this constant h. So light is a particle with energy quantized by factor of h, Planck's constant. So light was a particle according to the photoelectric effect. But, light did a bunch of wavy stuff as well. If we have a two-slit experiment, we see an interference pattern on the other side. These are fringes way zoomed in that appear on the screen here. So these are interference fringes. And these fringes still happen. If we got the light source so dim that we knew that only a single photon was going in at a time, we still get interference fringes. So even though light is a particle, we're shining only a single photon in this slit at a time, we still get interference fringes. And that's only possible if light is also a wave. So even a single photon produces interference pattern. because once that light goes through the slit, it eventually turns back into a wave, it interferes with itself, and we get a pattern. So light photon interferes with itself. Well, that's weird. We just said light was a particle. So the conclusion had to be light is both a wave and a particle. So the energy is confined in little packets h, but it depends on the wave-like property of having a frequency. So this was our first notion that, of a quantized little packet of energy. Later in the 1910s, 1920s, a dude named de Broglie came along. So enter de Broglie. I'm not sure how to pronounce French. He came along and he said, why does light get to have all the fun? Shouldn't matter be symmetric? And what he meant by that was matter, if light can act like a particle and a wave, maybe matter should act like a particle and a wave too. So he figured that matter should also have a wavelength, or a wave-like property to itself. He figured that, the wavelength should be proportional to h, the Planck's constant. And we knew that Planck's constant had units of angular momentum, joules multiplied by seconds. Or in other words, a kilogram meter squared per second. So what could I do to change a angular momentum into a, wavelength? Well, we know that just from classical physics that unit-wise, L, angular momentum, is a momentum times a distance. So if I divide h by momentum, I get the appropriate units of length that I want. And that's exactly what de Broglie hypothesized. He hypothesized that if I take an object with mass, matter, and multiply it by its velocity, then I get, and divide that into Planck's constant, I will get that object's wavelength. It turns out that most things with actual mass, because h is so small, that even if you're trucking at your maximum speed, I'll have you calculate your own wavelength in the checkpoint questions, but your wavelength is going to be very, very, very small. You're already taking 10 to the minus 34 and you're dividing it by bigger numbers than that. Your wavelength is teeny, teeny, tiny, tiny. However, when you get small things like electrons, their wave-like property, because of their small mass, becomes inherent. And even an electron with a kinetic energy of 1 electron volt has a wavelength of about a nanometer. So that's significant. That's a particle actually acting like a wave. And it turns out, if we do a 2-slit experiment, but now we shoot electrons instead of light particles, hey, we get an interference pattern. That's pretty cool. So these electrons are interfering with each other. And then they took it to an extreme. They said, what if we only shoot 1 electron at a time through the slits? And they still got interference pattern. So it turns out that single electron, just like a photon, will transform into a wave and interfere with itself to create an interference pattern. So this sort of verified experimentally de Broglie's hypothesis. I believe these were 2 guys named Davison and Germer experiment. They verified wave-particle duality for matter. We can decrease the wavelength. So it turns out if you want to resolve things, you're resolved by how well you can diffract into them. And essentially, by increasing the electron velocity, will let you get a smaller wavelength. So you can kind of think, if you're looking at electron microscopes, for instance, your pixel size, your resolution is dependent on how small your wavelength is. If I can accelerate those electrons faster, I can get, a more, pixel dense image showing all the features of the surface I'm trying to image. So we can relate an object's wavelength to its mass and its velocity. So if we take this idea of matter acting as a wave to its extreme, we eventually get to the Schrodinger wave model we mentioned earlier. And sort of quantum mechanics itself. I'm going to write the Schrodinger equation. You're definitely not going to be responsible for this. There's all kinds of dark calculus and magic in this equation, but to just sort of write it out to show you what we're working with. We have this equation here. This pitchfork looking symbol is the Greek letter psi, and this is the wave function. So now we are taking a piece of matter like an electron, and we are saying it's not a particle, but it is a wave. It is this sort of represents the probability of finding the electron at a certain position. So this equation takes the probability of finding an electron in a certain situation, and it tells you where it essentially will be as a function of space, or not where it will be, where a chance of it might being will be as a function of space. Sort of demystify this a little more. This function here clearly depends on psi, the wave function, but this term here, essentially in the beginning, is related to kinetic energy. This V here is sort of the potential energy of the system. And this E here is sort of the total energy of the state. So by sort of altering the kinetic energy of the electron and altering the situation, the potential that it's interacting with, you can change the energy of the system. That's all this equation is saying. We're not going to do anything more with it, but I thought you'd like to see it. So we are concerned with psi, though, wave function, what the wave function is doing. Typical example we do with quantum mechanics is sort of the particle in a box model, where essentially we have these very, very high walls that the particle cannot get through. They are what are called infinite potential walls. The particle cannot get through. But the electron lives somewhere in between these two barriers, and there's nothing else interacting with it. So again, the particle, is not a particle. It's not an electron moving back and forth. What actually manifests is that the wave function for this system, the most basic wave function we can get, looks something like this. The particle cannot be found at the edges of the system because that is an infinite barrier. The particle can't live at those regions, but it can live anywhere else in the well, and it's peaked at the center. What this peak tells us is that it has the highest probability of being found. So your question you might want to ask is the electron, is it here or is it here? And the answer is yes, it is. Like, the wave function tells us the electron has to be somewhere within this cloud of probability, so to speak. It's not until we actually measure where it is that the wave function, so we do a measurement. And it doesn't literally have to be taking out your quantum ruler and measuring it. It's any kind of interaction the electron might have. So you could say that, macroscopic matter barely acts like a wave because it's always interacting with other pieces of matter, causing them to sort of stay put. When I measure where this electron is in this well, we collapse the wave function and we define a single point of where the particle is. Now, when I make this measurement, the particle could be here or here. Based on the probability of being there will be sort of where you end up measuring it. So if we had like a million identical situations, each little well is the same, and we measured where the particle was in each one, most of the time we would find the particle dead at the center. That's the highest chance, but probabilistically speaking, we might find it fewer times at a region further away from that highest peak. So, the wave function tells where the greatest chance of finding the particle is. So in other words, here's our wave function. The wave function prescribes that we can't be at the edges. We're most likely to be at the center. Once we measure where that particle is, it could be anywhere within this cloud, but it's most likely to be where it is the highest. So we measure it, we get a little bit off center. If we were to do this experiment again with a different set, we might find it to be in a different place, but on average, where we find the particle should be centered around the center of this well. Just like with the atom, quantum systems can exist in a number of states depending on their energy. So, for example, we can get this would be the ground state, n equals 1. Here we have n equals 2, and our wave function looks decidedly different. So now we have sort of a full wave cycle. And note, before we were able to find the particle most likely to be at the center. Here, the amplitude of this function is 0 at the center, and the particle cannot be found there. No chance of being at the center. You'll also note the wave function itself is negative. It's a sine function, so it can take negative values. Being negative here does not mean there's a negative chance of finding it there, because what we're really looking at is the probability isn't psi, the probability is psi squared. There's an absolute value here because the wave function can be a complex number. Don't worry about that. But what happens when I square this function is all the negative values become positive, sort of the positive values, I guess, and we end up with a psi squared distribution like this. Again, there's no chance of finding the particle in the center, but there is an equally likely chance of finding it, a third of the way across and 2/3 of the way across. These are equally valid. So again, because the wave function is squared, what we're looking at is the amplitude of psi, not the absolute, or not the negative or positive value. So amplitude squared gives probability. N equals 3. You're going to see that these are exactly the same structure you might find on a standing wave on a string. Basically, the ends of this system are nodes, and therefore higher energy states are exactly the same shape and structure you'd find along, a vibrating string. So this is our n equals 3. If we square this function, we have sort of 3 peaks and 2 locations where the electron cannot be found. And so on. We could keep going up in values of n, and you'd keep getting more and more sort of loops along the structure here. But the main idea is that the higher the squared wave function, the more likely you're able to find a particle. So let's look at one quick example, and then we'll call it a day for today. So here is a more complicated wave function. So we have this wave pulse. And we are told that this has an amplitude of A, and this one has an amplitude of A plus some small amount, epsilon. If we want to figure out where the particle is most likely to be, we essentially have to square this function. So really, I mean, we don't have to draw the squared function. We know that any negative value squared is going to become positive, and it's going to be essentially larger than it was before. So this amplitude here gives us the most likely position. It would form at this amplitude here. So likeliest spot is where psi has largest amplitude. Even though this is positive, its amplitude is still smaller than this negative peak here, and therefore it is less likely to find the particle here than it is here, even though it might be a similar probability. It doesn't matter anything in this sort of x direction on this horizontal axis here. It doesn't matter how scrunched or compact this function is. This is a lot more compact and complicated than the functions we saw earlier. All that matters is the amplitude. So when you're looking at a complicated wave function, really you just want to look for the largest amplitude, and that is where the particle will be found the most likely. Any of these nodes here where the function crosses the x-axis, all of these zeros, the nodes represent no chance of being found. Even if we square those, 0 squared is still 0, and therefore you will not find the particle at those locations ever. All right, so that delves us into quantum mechanics. That'll do us for today. See you next time.